All right. So at first, I'm going to discuss the groups, the orthogonal group in 3 dimensions, both the special and the normal orthogonal groups. So let's see some of the properties in here, and then after that, I'm just going to look at these applications. So first, I'm going to yeah, let's just talk about this first. All right. So here, I'm just going to talk about these groups and the elements of these groups, some properties of the elements of those groups. And then I'm going to talk about some representations, some particular representations, all right? So in any case, let's remember this. O3 is the orthogonal group. It's basically the 3x3 orthogonal matrices. So whenever I say orthogonal, these are all real orthogonal, obviously. We know that these somehow correspond to some rotations. And then there are these 2 kinds. There are proper and improper rotations, depending on whether the determinant of the rotation matrix is +1 or -1. So the proper rotations form a subgroup, which we call as the special orthogonal group, if you remember, right? And we just, yeah, whatever, we just call them like that. So in any case, here the distinction is actually quite simple, but I'm going to start with this basic SO3 thing. So let's say it like this. Let R be a proper rotation. Right? R is an element of SO3. It's a, yeah, whatever, it's a rotation. In any case, so in that case, I'm going to show that R has, the matrix R has an eigenvalue. Has a +1 eigenvalue, right? Let me write it down like that. Has a +1 eigenvalue. So one of the eigenvalues of that matrix is +1. I'm going to tell you the significance of that, actually, because the corresponding eigenvector is basically the rotation axis, all right? So that's what I'm going to prove in here. So I'm just going to, first of all, doing the proof. So let me just list some of the properties. So let's say that, so this is a 3x3 matrix, so therefore it has 3 eigenvalues, its eigenvalues, right? So I'm just going to call the eigenvalues like that. So I know that R is orthogonal, so therefore it is unitary. Right? It's a real unitary, right? An orthogonal matrix is real unitary. So that means eigenvalues have modulus 1. I mean, we can show this in other ways as well, mathematically in a precise way as well. And it's basically the norm-preserving property of the unitary matrices. But I'm just going to leave that to you. So as a result, each of these numbers have modulus 1. So therefore, these are numbers on, let's say it like this, e to the I phi I. So they are basically on the unit circle on the complex plane. So each of the eigenvalues are like that. And of course, there is also the diagonalizability issue that, I mean, it really has these eigenvectors and the corresponding eigenvalues and the corresponding eigenvectors. But in any case, I don't need these kind of details. All right. So that's the first property. Because the matrix is orthogonal, all the eigenvalues have modulus 1. The second one is this, right? R is real. So that means the complex conjugate of each eigenvalue is also an eigenvalue, right? Let's say it like this. So, I mean, think of it like this. R applied on an eigenvector, let's say Vi, is equal to lambda I times Vi, takes the complex conjugate of that equation. So that's lambda I star Vi star. If you take the complex conjugate, but R is already real, so therefore its complex conjugate is equal to itself. And yeah, that's the reality property. Sorry about that. Right? I'm just going to write it in here. R is real, so it's the complex conjugate of the matrices, whatever. So that means if I apply R to the complex conjugate of the eigenvector, I get, yeah, whatever. I still get the same eigenvalue equation, but with a different eigenvalue now. It's the complex conjugate. So that means, so if lambda 1, lambda 2, and lambda 3 are eigenvalues, then their complex conjugates are also eigenvalues. Right? So that's the second statement. Right? So that means, in particular, that for every I, the complex conjugate of the ith eigenvalue is basically equal to some other eigenvalue. So as a result, there are actually two possibilities in here, or many possibilities. So if lambda I is, let me just write this thing down. This is the unit circle on complex plane. So let's say this is x-axis, this is y-axis. Right? So that's the unit circle. If lambda I is in here, in the form of e to the I theta I, then this complex conjugate is in here. So therefore it is in the form of e to the minus I theta I. Right? So that's lambda j then. So therefore, if the eigenvalue has a non-zero imaginary part, right? It's complex. Then its complex conjugate is different, so therefore this is going to be one of the eigenvalues. So as a result, once I have an eigenvalue like that, I can find the other eigenvalue here, right? But there are these two special eigenvalues, +1 and -1. Their complex conjugates are themselves, so therefore their complex conjugates give themselves, right? As a result, in this equation, therefore, I and j indices would be the same. Right? Think of it like that, right? But I'm just going to write one more thing. So I know that R is in SO3, so that means the determinant of R is equal to +1. So that means the product of all of these eigenvalues is equal to +1. So I'm going to join all of these facts and show that one of the eigenvalues have to be +1. Okay. So as a result, I mean, I'm just going to say there are three possibilities for eigenvalues. Okay. So lambda 1, lambda 2, and lambda 3 can be equal to, so it is possible that there is a complex eigenvalue like that, where theta, well, it's somewhere in here on the unit circle, right? Let's say it like this, in which case, e to the minus I theta would also be an eigenvalue. So therefore, if lambda 1 is this, then lambda 2 would be that one, which means that the last eigenvalue can only be equal to +1. Because only in that case, you are going to get the product is equal to 1, right? Because already the product of these two eigenvalues is equal to 1, so therefore there's only one possibility for the last eigenvalue. Or there's the second possibility. In that case, none of the eigenvalues are complex, so all of them are real. So they can be +1 and -1. So if there are negative eigenvalues, they should be repeated so that the product is equal to 1. So that satisfies still. Or if there are no -1 eigenvalues, then all of them will be +1. So in that case, the product rule is satisfied, right? So these are the only three possibilities for the set of eigenvalues. Okay. So I think at this point, I'm going to say that the last two possibilities in here is actually a very special case of this situation. If I also extend the definition of um, theta to include theta equals 0 and theta equals pi, right? Or let's say we can say that just a moment, let me think about this. Or we can say that R has eigenvalues, let's say e to the I theta, e to the minus I theta, 1, where theta can be 0, in which case I'm including this possibility in here, or less than pi, or equal to pi, sorry. And if it's equal to pi, then I include that possibility in here. So in any case, so in this case, the first two eigenvalues would be equal, but for all other theta values, then we are going to have this situation here, right? So in summary, I can say this, and probably this is the best way that we can deal with this result. So that's true for any rotation in SO3, okay? Any rotation, whatever it is. So it turns out that this one corresponds to identity, okay? Because all of the eigenvalues are equal to 1, this is an operation, and all of the all of the vectors in the spaces are eigenvectors of that operation. So therefore, this is basically the identity, right? So it appears that this one is basically a 180-degree rotation. Basically, it's some kind of an inversion along two axes, like x and y axes, let's say. And it turns out that this is a rotation by theta. Okay. So as a result, you can see that the identity and this 180-degree rotations basically is just a special case of this. Right? In one case, the rotation is by 0 angles. In the other case, it's 180 degrees, right? Let's just say it like this, okay? In any case, what's important in here is that one of the eigenvalues is equal to 1, right? That's basically the end of the proof. That's what we wanted to show, right? That's basically our starting point. Yeah, what was it? Yeah, so that was the theorem, right? For any proper rotation, +1 is an eigenvalue. What does that mean? There's a corresponding eigenvector. Let R be in SO3, right? So let's say that let N be, I'm just going to take this as a unit vector. So let N be the eigenvector corresponding to +1 eigenvalue. Okay, so therefore Rn is equal to n, right? So you can easily see that the complex conjugate, if that vector is complex, then the complex conjugate would also satisfy the same thing. So by the uniqueness of the eigenvector, I'm basically considering the situation in here apart from identity. So let's say it like this: if R is different than identity, okay, then eigenvector is unique. Which means n star is basically some constant times n, which means, let's say I can choose n real. It's basically a real vector, right? There is some kind of a real vector. So that's what I'm going to assume, that n is a real vector here, right? So this implies that, this Rn implies that n, so n is left invariant by rotation, right? So as a result, because of that, I just call this as N as the rotation axis.
Joe, may I ask something?
Yes.
Yeah, can we do this in SO2? For instance, can we choose an real N, which is invariant, left invariant in
In
SO2?
SO2, the eigenvalues are e to the I theta and e to the minus I theta. There is no
Yes,
plus one eigenvalue.
right. That's correct. Yeah. Okay. Okay. Thank you.
I mean, in even dimensions, we don't need to have a plus one eigenvalue. For odd
And that's
dimensions,
correct.
there should always be a direction in which, yeah, this is true for on spaces with odd dimensions. There should always be an axis which is left invariant, and this is what we see in SO3.
Okay. Thank you.
Mm-hmm. Okay, so that's the rotation axis. So I sometimes do this, so let's just keep in mind that minus n is also a possible rotation axis. Just keep this in mind. So it's not the direction, it's basically the line. Right? So since we are just looking at this property that this n is an eigenvector, minus n is also an eigenvector. I'm just going to normalize it, but still with the normalization, there's some kind of a freedom in the choice of the vector that represents the rotation axis, right? But in reality, it's not a vector, it's an axis, it's a line. But of course, we use this thing. Okay, so in any case, so that's the rotation axis. So there is this two-dimensional plane which is perpendicular to this rotation axis. So let me call this as, I don't know, let's say V is the 2D plane perpendicular to M. Okay, so I know that if there is a vector in that plane, so let me call this as a V in here. So this vector is perpendicular to M. So let's say V is perpendicular to M. I know that the orthogonal transformations does not change the angle. So therefore, V rotated by R is still perpendicular to M rotated by R, but M doesn't change under rotation. So that means this RV is still within that plane, right? So that means RV is still in this plane. So that means R transforms, yeah, let's say R rotates vectors in V to vectors in V. Okay, so as a result, from that point on, you can think of this as this rotation as a rotation of like the SO2 rotations within that plane, right? Basically, the I mean, at this point, it's just a two-dimensional rotation. Once you actually throw away the rotation axis, you're just left with this. So as a result, what we have said about the rotations in two dimensions is going to be valid, right? So this is a proper rotation in that two dimensions. So therefore, there's some kind of an angle in here. And that angle is exactly the same as the angle that appeared in the eigenvalues, right? But I'm not going to go into the details. But I think if I remember correctly, for rotations in SO2, I have deduced this, I have found these eigenvalues. And from here, you can easily see that that theta is the eigenvalue. That theta is basically is the rotation angle, sorry. Right, in any case, so as a result, every rotation in SO3 can be thought like that. So as a result, there's a special notation in here. So I'm just going to use the right-hand rule in here. Right-hand rule. Basically, what I do is this, so that's my right hand. I keep drawing these right hands in this general physics courses as well, right? This is my right hand. So what I do is, if my thumb shows the direction of the rotation, the four fingers show the direction in which I would measure angle theta. Okay? So as a result, then by a rotation around and by angle theta, I mean this rotation in here. So let's say it like this. This is the rotation by angle theta around axis M. Okay. What is interesting in here, sorry about that. I'm going to draw another right hand, but this time the thumb shows the downward direction. How can I do this? So it's like that, right? So I think it's going to look, I think it's going to look like this, right? These are my four fingers. And this is my thumb that shows the downward direction, right? Is this correct? Yes, it's correct. So if my thumb shows the other direction, minus n direction, in which case I have to measure the angles along that direction. So as a result, if the rotation corresponds to a positive theta in here, it should correspond to a minus theta in here, right? I'm just going to give one example in here. So that's the same thing as, sorry about this. So that's basically the same thing as a rotation by angle minus theta around axis minus m, right? So as a result, this rotation around m by theta is the same thing as rotation around minus m by minus theta. So because of this peculiarity in here, there's some kind of a freedom in the choice of the unit vector that represents the rotation axis. I have a choice in that. I have two possible choices. So as a result, to express the same rotation, I have these two symbols in there, right? But in a moment, I'm just going to simplify this. Okay, so it's just an example, right? So that's the x-axis. This is the y-axis. This is the z-axis. So think about the rotation around the z-axis by 90 degrees, right? Plus pi over 2 radians. I'm just going to show all the angles by radians. So that's the natural unit, remember. So in that case, for example, this one is just a rotation around this z-axis. You just need to use your right-hand rule, your right hand carefully. So that transforms x into y into minus x, sorry, y into minus x, and leaves z invariant, obviously. Okay, think of it like that. So in this case, I'm using the positive z-axis as my axis, and by the right-hand rule, positive 90-degree rotation will basically carry the x-axis into y, right? Let's just keep this in mind. I can also think, so I'm just going to draw the same picture. Let's choose the rotation axis is the downward. I'm just going to represent the same rotation. Sorry about this. So this is my rotation axis. So that's my n vector, for example. In that case, it's a rotation around minus z, okay? But try to imagine this, this rotation in here. This is a rotation that carries the x-axis into y. So therefore, this is a negative rotation, right? So that's a minus pi over 2 rotation. Try to actually understand what I'm trying to say in here. So that carries x into y into minus x, and z into z again. So as a result, these are two the same rotations. Okay. So a positive 90-degree rotation around z-axis is the same thing as minus 90 rotation, minus 90 rotation around minus z-axis. Okay. So in this case, I can take, yeah, let me quickly do this. So I think I'm just going to, I didn't want to enter into this topic at this early, but in any case, let's just do it like this. Um, so is there, I mean, this is the basic fact in here. So I can express a given rotation by using this axis like that, or by using the opposite axis like this. So what's interesting in here is that if I define the product of these two vectors and call it as some kind of a theta vector, I mean, sorry about this, the product of the angle with the rotation axis, right? I'm multiplying the angle with the rotation axis, in which case, since I know that minus theta multiplied with minus n gives me the same thing, in that case, we don't have any ambiguity in the notation. So as a result, I can express the same rotation with a three-dimensional vector, right? So in any case, let's say it like this. So we can express any rotation R in SO3 in terms of a vector parameter theta. So R is basically some kind of a rotation by angle theta. So therefore, there are three parameters in here. The x component, y component, and the z component of that theta vector, right? So that means SO3 is a Lie group with dimension 3, because I can parameterize the rotations by three parameters, right? Or you can think of it like this: a unit vector is, you can parameterize a unit vector by two parameters, two real parameters. It's like the azimuth and zenith angles. And theta is the third parameter in here. You can also count the parameters like that, but I think this is a little bit more convenient. Okay, so let me quickly go to this one too. All right, so unfortunately, this theta is not unique. Note, theta is not unique. Why? Because a rotation by angle theta is the same thing as a rotation by angle theta plus 2 pi. Sorry. And so therefore it's a rotation by angle theta plus 4 pi and so on. All right? So that means I can use, I mean, for the same rotation, R, I can use a theta vector, which is theta n, or I can use a theta vector, which is theta plus 2 pi n, and so on. Right? I can basically, if I parameterize the rotation by a vector, I find infinitely many vectors in there, right? That's some kind of a problem. So for example, identity, that's kind of the interesting one. So identity I is basically a rotation by zero angle. The rotation axis can be anything. So as a result, this is basically also can be described as a 2 pi rotation around any angle, or a 4 pi rotation around any axis, and so on. Okay, so identity is somehow this special place as well. Okay, what we do, people usually do not like uh, things being parameterized with many different ways. So as a result, we just constrain this, right? So as a result, we basically find for a given rotation, we find an angle which is basically less than pi. Then in that case, I find a unique vector in here. Right? So let's say it like this. If we constrain the value of theta such that theta is less than or equal to pi, and theta such that, then we can find a unique theta for almost all rotations. I'm adding almost because I'm going to explain this in a moment. Because the point is this, I mean, think about this. So this is zero. This is theta equals 0. Think about this as a sphere of some kind, right? It's not an arbitrary sphere. It's a sphere with radius pi. So, right. So let me say it like this. This is a sphere with radius pi. Okay. Think of it like that. So as a result, let's just think about some kind of a rotation. If it is identity, then I know that the angle can be either 0 or 2 pi or 4 pi or whatever, but within that sphere, there's only one point that corresponds to that rotation, and it's basically the central point, right? So that corresponds to theta equals 0. So that's the identity, right? So let me erase this because I would like to add something more, right? So this is theta equals 0, which basically corresponds to identity. Okay, and think about any other rotation with an angle less than 180 degrees, right? In which case the theta angle is less than pi. So as a result, I can find a point in there. So that's theta n, let's say. I know that all of the other equivalent rotations are outside. So theta plus 2 pi would be somewhere in here. It's going to be basically along this axis. And so you can basically see all the other equivalent vectors to that rotation. They are all outside the outside sphere, right? So as a result, for most of the rotations, I can find a unique point in here where this theta vector is within that sphere. There's an exception in here. If the rotation is at the surface of the sphere, in which case, yeah, let me show the surface like that, all right? This is basically, this point has a distance of pi from the center, so therefore this is a rotation. So this is an angle, sorry, this is a vector which is pi times n, so that basically corresponds to a rotation by 180 degrees. But I know that this diametrically opposite point on the other part of the surface, this is called an antinodal point, is minus pi n. And I know that a minus pi rotation is the same thing as a pi rotation because they differ by 2 pi. So therefore, these two points are basically represent the same rotation, right? Let's say it like this. So this pi n and minus pi n are what we call as antipodal points. Think of it like the Earth, like you are somewhere in here on the Earth, let's say, this is the point in the opposite side of the Earth. So probably for us, it's somewhere in some ocean, but I don't know where. In any case, so these are called antipodal points. So let's say it like this. On this surface, so antipodal points of this sphere correspond to the same rotation. Okay? But all points within the sphere correspond to a unique rotation, right? So somehow, let's see it like this. The points on the surface, sorry, the points inside correspond to a unique rotation in SO3, but for the points on the surface, the two antipodal points correspond to the same rotation, but different sets of antipodal points correspond to different rotations because the rotation axis is different, right? So that's basically the difficulty in here, right? So let's say it like this. Inside points of this sphere correspond. Let's say it like this. Each inside point of this sphere correspond to different rotations of SO3. Okay. So as a result, this is the manifold representation of SO3. Okay. This is kind of complicated. It's actually a sphere, and there is no problem in the inside. It's a problem in the surface. So, I mean, somehow you have to remove this ambiguity at the surface, and we do this in topology of what we call as some kind of an equivalent, making some points equivalent to each other or something like that. Let's say it like this, right? So that's the manifold representation of SO3. So this is some kind of a way of picturing the rotations in the SO3, right? This is basically a sphere. Sorry, this is a sphere with radius pi with antipodal points at the surface identified, right? So let's say it like this. This is a sphere with radius pi where the antipodal points at the surface are identified. Sorry, identical. Well, they correspond to the same rotation, okay? So this is a complicated topological structure, right? I mean, if it was just a sphere, there would be no problem, right? But once you do this identification, there are some complicated things going on. So for example, suppose that you would like to think of it as some kind of a space, a space. And you're a creature living in that space and you're moving around. So suppose that you start moving from the origin and then you wander around within that set. And whenever you reach to that surface point, it means that you're still, you are also at the opposite point in here. So when you are crossing that point in here, if you just move straight ahead, this is the same thing as crossing like that, right? Okay, so as a result, when you go out of the surface from here, you basically enter from that part, right? There's some kind of a complicated periodic boundary conditions in here, right? I mean, it looks like the surface of the sphere is some kind of a boundary, but it is not. You can cross this surface but when you cross, you just come back from some other place. Okay. So as a result, this is a little bit complicated picture in here, right? In any case, so that property is very important for the structure of this the group SO3, because somehow it is related to something. Yeah, I'm just going to talk about this later, right? On Wednesday, probably. So let me just leave it in here. Okay, so somehow we obtain some kind of a picture of this group SO3 as some kind of a topological manifold, right? It's basically a sphere, but there's some kind of a strange boundary conditions applied at the surface so that it looks complicated. It is hard to visualize because of this. I mean, I can do this easily for one-dimensional things like, I mean, if I have like a one-dimensional line where this point, for example, is identified with that point, for example, and I say that the space is basically this space where, but this point is identical with that point, I can basically do it like this, imagine it like this. I just bend it in the form of a circle and just join these points 0 and 1 and just place them on top of each other, in which case I basically get a circle, right? So as a result, the topology of this kind of a structure is very simple. But you're doing this identification in 3 dimensions. So as a result, we don't have any simple picture like that to fully understand what's going on here, right? So the topology of this one is it's actually very complicated, okay? So on Wednesday, I'm going to say that there's some kind of a hole inside this topological space, but it's a very peculiar hole. When you go around this hole once, the hole is there, but if you just go around twice, it somehow disappears, right? But in any case, it's kind of an advanced mathematics, so at this stage, I'm not going to say anything. Okay, so this is about SO3. Right? What's important in here is that I mean, if there's a rotation in SO3, you can think of this rotation as a rotation around an axis by an angle theta. Right? It is as simple as that. Now let's go to O3. Okay. Well, within that group, so there are these improper rotations. So there's actually a very special improper rotation. So that's called the inversion. So that's this matrix in here, where all of the eigenvalues are equal to -1. That's minus identity. So J is called the inversion. Some people call this as parity. No, it is not. I mean, the correct name is inversion. Parity is basically the eigenvalues of some representations of this inversion operation, right? But I mean, it is something which is related to parity, right? So in terms of an operation, so an inversion basically just takes a vector like the position vector, for example, and transforms it to its inverted form. So it just, I mean, it just takes a vector and then inverts it, right? Think of it like this. So this is the same thing for momentum as well. I'll talk about this in some detail in the second hour, right? So that's the minus P. Okay, so let's say it like this. J is an improper rotation. So that means J is an element of O3 and J is not an element of SO3 already. But it's an orthogonal matrix as a matrix. Okay, so that's what I'm trying to say. What is nice in here is that the product of 2 improper rotations is a proper rotation. So as a result, I can basically express any improper rotation as a product of J with a proper rotation. So let's say it like this. I think I'm going to use this XYP. Let me use this symbol, let's say Q, right? Let's say it like this. Every improper rotation Q can be written as a product of a proper rotation R and inversion J. We have, I think we have also said something similar in the case of the 2 dimensions. It's the same in 3 dimensions. So I can write down any improper rotation as this inversion multiplied with R, where the determinant of R is equal to +1, right? But Q has -1 determinant. So the nice thing in here is that J is equal to minus I density. So therefore, I can write this in any order. So J commutes with every proper rotation. It commutes with everything, every rotation actually, proper or improper. Yeah, I think that's it, right? There's not much else that we can say in here, which then tells us that this part of SO3 can be written as, let's say it like this. Sorry. So therefore, O3 can be written as, it's basically the union of the proper rotations and J multiplied with the proper rotations, right? I can also write it down like that. So these are proper and improper. I think I'm writing some unnecessary things in here, sorry, and I don't actually want to mean that. But the important point in here is that J basically commutes with these elements, so therefore the order is not important. So therefore, I can write this, O3 can be written as the product of this group, which is basically a 2-element group, product with direct product with SO3. Okay, that's basically what I mean, right? So what I have written down in here is basically the same as this one, but expressed with the proper group terminology, right? So, I mean, the correct way of actually expressing is that this O3 is isomorphic to the direct product of the cyclic group C2 multiplied with SO3. Okay. Moreover, we also have the opposite relationship. So this quotient group. So, I mean, I have done this discussion at the beginning of the semester, but I don't want to repeat it in here. Right? O3 and SO3, the quotient group is equal to cyclic group. And just remember that it doesn't matter whether it is O3 or O2, the dimension doesn't matter. So the quotient of the orthogonal group to the special orthogonal group is always equal to C2. Because I think I have made a discussion of this thing, right? Now, what's interesting in here is that this product relationship is not valid in 2 dimensions. And I have mentioned that before. So O2 is not isomorphic to the direct product of C2 with SO2. And I think I have explained the reason there. I have said that SO2 is abelian, this is abelian, their products are abelian, but O2 is not abelian. And so as a result, we don't have this kind of a relationship in there. But in the 3 dimensions, we have And that's kind of a very special to the 3 dimensions. It's actually very special to odd dimensions, all right? So in odd dimensions, we have the quotient relationship and the product relationship. These are satisfied. In even dimensions, they don't. And try to remember why this is the case, right? In 2 dimensions, this inversion thing is not an improper rotation. It's just a rotation by 180 degrees, if you remember. So there were no inversion like improper rotations, but there were some like things like reflections, but the reflections were not commuting with the other rotations, and that's the critical part. So here we have some kind of an improper rotation, which is the inversion. It commutes with every rotation, so this relationship is satisfied, so therefore we can say this for the group structure. All right, again, this is some kind of a theoretical discussion, but what is important in here is that this rotation group O3 has a very simple structure. Okay, so it is different than the picture in the 2 dimensions. In 3 dimensions, the improper rotations are kind of very simple, right? I think that's the only thing that you have to remember. That's the important point. But I mean, using the facts that we have said about the rotations in SO3, we can actually say this. So I don't know, we can say things like, let's say if Q is improper, then Q has a -1 eigenvalue. For any improper rotation, I can say this, which means that there's some kind of a plane in here. Sorry, there's some kind of an axis in here. So this axis is such that if Q is applied, this axis changes direction, which means that the plane perpendicular to the plane is what we call as a mirror plane. Right? It's called a mirror plane. So you're doing some kind of a mirroring in there. But moreover, Q has the effect of a rotation in a proper rotation in this 2-dimensional plane, right? You can describe any improper rotation like that, but again, I mean, that's not that. It's not that important actually. I think there are some special names given to these kind of mirrors where there's some kind of a rotation in the mirror plane, but I don't know. I don't remember the name actually. Okay, so let me leave it there, right? So in the second hour, I'm going to go to the representation theory. I'm just going to talk about 2 particular representations of the group O3. And then using this, I'm just going to, I think I'm going to do some fun things about some strange terminology. All right, so I'm just going to keep it as a secret at this point, right? So let me have a break. So let's meet at 11:40.